This is section 3.6, a summary of curve sketching. Okay, so this is what a lot of our work has been going towards, is being able to sketch the graph of a function by hand or even with a graphing utility. Remember that when you do this on a graphing utility, you normally can't see the entire graph. And if you accidentally pick a window where you can't see all of it, you might not know that that's not all of it. So let's say that you had a function and you graphed it in this window and you saw this. You might think, all right, it's a parabola and I got it. But in reality, if you were to zoom out some, that's actually part of this graph. And of course, you didn't know that that was there. Well, what could have helped you to know what was going on with this? Well, calculus could have found all of your relative extrema. So you would have known to look for these 2 points, and you could have adjusted your window so that you'd make sure you see at least those. If you know the end behavior is up on the right and down on the left, you never would have accepted this as the end behavior. You would have been looking for something on the left that goes down. So this would not be your end behavior, and you'd need to expand out to get a good window. And calculus can help you do that. If you know where your relative extrema are, you can certainly make sure every one of those is pictured. If you know what your end behavior is, you can make sure that you can see that. Now, another problem that you might have is you may think that when you graph something, you've got the whole picture, that you see this and you think, wow, I am done with this. This looks wonderful. And unfortunately, if you were to zoom in right here on the graph, what if there were something going on in there that you weren't even aware of? Something like that you had no idea. Well, again, if you knew, for example, that it had relative extrema there and changed from decreasing to increasing at that point, and then from increasing to decreasing at that point, you would know you need to look for that, and that you couldn't just accept this, what looks like a cubic curve and perfectly fine. Maybe not. Maybe there's that little bitty behavior in there that you can't see. So graphing technology is great as long as you can find a good window to see everything you want to see. And that's part of the challenge. So calculus is still used for even graphing with graphing calculators. Now, what we're going to assume for this section is that you're still working on how to graph a function without technology. So you're going to have to be able to graph a function by hand using everything we've talked about. I'm going to give you a long laundry list of things to think about and look at. And on the test, I would list all the things I want you to make sure that you address and then draw the sketch without a graphing calculator in your hand. So looking at figure 3.44, you have f of x equals x cubed, etc. Which one of those seems correct? Well, you know that the cubing function has up on one side, down on the other. And because the leading coefficient is +1, the right side's going up. So obviously the one to the right is better because the one on the left doesn't show that upward behavior on the right-hand side. Okay. So, is it possible that neither of those is actually a complete picture? Is there maybe something going on? Well, to answer that question, calculus is really your best friend to answer that kind of thing. So, to determine a good viewing window for a function, use these guidelines to analyze its graph. Find the domain and range of the function. Make sure that if you're going to indicate end behavior, you have to make sure, like this part of the graph over here, that if it's going to be up on this end and down on that end, that you can see that going on. Again, so knowing the domain and range and the end behavior can help you make sure that you're getting a full idea of what's going on. To determine the intercepts, asymptotes, and symmetry of the graph, that can make sure you're not forgetting half of it. For example, if there's symmetry and you can't see the symmetry, you obviously don't have the whole graph. Asymptotes are essential for you to get all of those in there. And intercepts, of course, when the axes are visible in there. If you cross one of those axes, that should be indicated on your graph. Finding the x values where the first or second derivative, either one is equal to 0 or doesn't exist, are potentially relative extrema for first derivatives and points of inflection for the second derivative. And so having those points clearly found is a good idea. And so that's kind of the broad scope of what you should make sure you do. So I'm going to go through a long laundry list on this example, some of which you may not have to verbalize on the test. You may just need to think about it. But I'm going to hit every topic that I can think of for this one to make sure that every single aspect of this is covered in detail. Okay, so one thing I would do to get started in talking about domain and range is this is going to be easier in a lot of ways to figure some things out if it's in factored form. If it's not in factored form, you might want to start by factoring. There'll be some things for which the factored form is actually a nuisance, but for some things it's actually very, very helpful. For example, in factored form you can tell that nothing will cancel, which means you don't have any removable discontinuities. So if I ask you, are there removable discontinuities, or find all removable discontinuities, you would address that by saying there aren't any. There are no removable discontinuities. And that little statement I just wrote is sufficient for that. Then when you look at the denominator, after all canceling has been done, you'll be able to locate vertical asymptotes. Any number that makes the denominator turn into 0 after you've reduced the fraction will give you a vertical asymptote. And each one of these is its own asymptote, and I'd like one equation for each asymptote. Don't put a x equals plus or minus 2 here. I want it to be very clear that there are two separate asymptotes here. So that's actually giving us a little bit of an idea about domain, which is one of the things you should address, or at least in your head. We always assume that you can use every real number, and then take away the things that you can't use. For example, anything that would make you divide by 0 you can't use, or anything that would make you take the square root of a negative, for example, you can't use. So you can't use 2 and you can't use negative 2. So your domain is going to be all numbers that are real except for negative 2 and 2. And so this is a statement that indicates all real numbers except for negative 2 and 2. Now the range is something that a lot of times you can't just look at the equation and tell someone what the range will be. A lot of times if I'm asked what is the range, I'm going to come back at the end after I've done the graphing and everything and talk about the range. So I'm hoping I don't forget to go back and do this. I'm going to go ahead and write the answer, but you're not going to know how I got it. And I'm going to pretend, this is just to pretend like I'm coming back later and filling this in, because I don't want to forget to give you the answer for this. So pretend after we've graphed that we've come back and found this range. And you'll understand where it comes from, not with what I'm doing right now, but from work we'll be doing towards the end of the problem. So there's the range answer, and I'll come back hopefully and talk about that and not forget to say something. Okay, so x-intercepts occur when y is 0. So set the function equal to 0 and You should know that the only way a fraction can equal 0 is if the numerator is 0 and the denominator is something not 0. Because if it's 0 over 0, that's an indeterminate form. And here that would lead us to a removable discontinuity, which we don't have. So setting this equal to 0, the only way that can happen is if the numerator is 0. So that means that 2 times x plus 3 times x minus 3 would be 0. And so that means that the x-intercepts are -3 and 3. The y-intercepts occur when x is 0. So substituting 0 in, you'll get -18 over -4, which is 9/2. Notice I'm saying that the intercept is a number. Intercepts are places on the axis where the curve touches the axis, and so that's a numerical value. Some people will call it the point, and that's sort of right, but if I gave you an equation y equals 3x plus 7, I said, hey, what's the y-intercept? You're probably going to say 7, right? Because you were told y equals mx plus b. B is the y-intercept. That's a number. So that maybe that'll help you remember that intercepts are best stated as numbers, not points. Now, we already did vertical asymptotes. To find horizontal asymptotes, if there are any, and this is a rational function, so there might be, I'm going to take the limit as x approaches infinity of 2x squared minus 18. You see how I'm playing with the form? I'm using the form that I think would work best. So you know the trick that we talked about is, since those powers in the numerator and denominator, if the greatest power of x is 2, they're equal, the answer will be the ratio of the leading coefficients of those two polynomials. So 2 over 1 is what I'm expecting this to be. But I want to show that work. So I'm going to find the highest power of x in the denominator, x squared, take its reciprocal, 1 over x squared, over itself, 1 over x squared over 1 over x squared, and rewrite this after distributing as 2 minus 18 over x squared over 1 minus 4 over x squared, and the limit of the constant 2 is 2. The limit of a constant over a positive power of x as x goes to infinity is 0, and same ideas in the denominator, and so that is 2 over 1, which is 2. So that expectation we had actually ended up being correct here. So if it had been negative infinity, would I have changed anything? I would still use 1 over x squared for both of those. And over here, 18 over x squared, as x goes to infinity or negative infinity, it will still go to 0. Same thing for the denominator, 4 over x squared thing. It would still go to 0. And so I've actually captured both sides. And so what we will have here, because of the work we've done, is that we know we're going to have horizontal asymptotes on both sides at y equals 2. Okay, symmetry. The test for symmetry. Let me tell you what the test is first, and then we'll perform the test. So this isn't actually part of the work for this problem. I'll box it in a second. There are two types of symmetry that we're going to test for. Symmetry with respect to the y-axis is one of them, and symmetry with respect to the origin is the other one that we're going to test for. There may be other symmetries out there. I'm not saying that we'll find all symmetries. With this, we'll just find these two in particular. So the test for symmetry with respect to the y-axis is because all even functions do that. It will be an even function, which means that when you substitute negative x into the function, you'll get back the original function. So again, that's all even functions have symmetry with respect to the y-axis. And we'll pass this test that f of negative x equals f of x. Symmetry with respect to the origin happens if you put negative x into the function and get back exactly the opposite of the original function. It will have symmetry with respect to the origin. And of course, that's the test for odd functions. And all odd functions are symmetric with respect to the origin. So let me box this in. This is kind of informational. It's what you're going to use. So it's not really in the flow of the problem. Kind of instruction in the middle of doing this problem, if you will. Okay, so I'm going to put the opposite of x in to our function. So that's going to be 2 times the opposite of x, replacing x, squared, minus 9, over negative x, replacing x, squared, minus 4. Well, the opposite of x times the opposite of x is simply x squared. In both places. And that actually gets me back to the original function. So we found that this is an even function, and as far as symmetry is concerned, we'll say it's symmetric with respect to the y-axis. Okay, so that's actually kind of the end of the pre-calculus part of this curve sketching thing, because these are all things you've heard about and talked about before. We're finding the horizontal asymptotes with a limit, which may be new for you. But other than that, this is all basically pre-calculus level information. So all of that stuff you should have been able to find before you took this class. Now let's talk about the things that you learned in this class. The first derivative. Okay. So for the purposes of finding the derivative, I think maybe I should write down what I'm thinking instead of just saying it. Oops, hold on, that's wrong. Sorry, you can't see what I just did, but I know I did something wrong. I'm going to find the derivative, but I'm going to rewrite the function as I did it at least one time before. I'm going to distribute the 2 for the purposes of doing the derivative. I think it's easier in this form. Okay, so f prime. Since that's a quotient, I'm going to use the quotient rule. So low d high minus high d low all over the square of low So let's do some simplification. See, that's 4x cubed minus 16x minus 4x cubed plus 36x all over x squared minus 4 squared. And that simplifies to be 20x divided by, and I'm going to write this in factored form. X squared minus 4 is x plus 2 times x minus 2. And if I square that, I can distribute that squaring over both factors. And so they'll each be individually squared. And the reason I'm writing it in that form, it's the factored form, is this final version of the first derivative I want in factored form. So when I set it equal to 0, or when the first derivative doesn't exist, which is of course how we're going to find our critical numbers, it actually doesn't exist if the denominator turns into 0. And that'll happen when x is negative 2 or when x is positive 2. And the fraction equals 0 only if the numerator equals 0, which means x equals 0. So we have three critical numbers, negative 2, 0, and 2. So I'm going to do the number line analysis for the first derivative, which will give me information about that behavior of our function. And our number line will have all of these numbers in numerical order from lowest on the left to highest on the right. So negative 2, 0, and 2. The one I got from equals 0 is 0, and I'm putting a solid dot there. And I got negative 2 and 2 from doesn't exist, so I'm putting an open circle there. And that's a reminder to think, wait, there's something different about negative 2 and 2, so don't jump to conclusions about points there, because there might not be any. In fact, those aren't in our domain. So if we decided that, let's say that the function increases to 2 and then decreases thereafter, there's no maximum there, because there's not a point there, there's a vertical asymptote. So circling those helps remind you not to do something silly, like assign a relative max to be there when that's impossible at a vertical asymptote. Okay, so now if you look at the denominator, both x plus 2 and x minus 2 are squared, and that means that those two items produce positive results, except at 2 and negative 2 where it's 0 and that won't work, so ignore those. So the denominator is always positive. So the only thing that's going to change whether the whole derivative is negative or positive, it's all determined by whatever the numerator is doing. So if I pick a number like negative 3, 20 times negative 3 is negative, and negative divided by always positive is certainly negative, which means the function is decreasing. From negative 2 to 1, from negative 2 to 0, pick negative 1, for example. 20 times negative 1 is negative, and of course the denominator is always positive, so it's also decreasing there. And at 0, from 0 to 2, let's pick 1. 20 times 1 is positive, divided by always positive is positive, and beyond 2, that will also be positive, and the function will increase and increase. Now, if the question had asked you to find where the function is increasing and decreasing, and that was kind of the end of the question, I would say please write those sentences. F of x is decreasing on the interval from negative infinity to negative 2, open, union negative 2 to 0, open for both of those. because f prime is negative on those intervals. And then the same kind of thing for increasing. Here, where the bigger idea is the graph, and this is just one of the many components of it, I'm not going to look for those sentences. I'm going to have this number line analysis tool that we've just done kind of speak for itself, and you won't have to write sentences. But there's one other thing I would want you to identify, is if there's a local max or local min. And if you look at 0, which is actually, there is a point on the graph at 0, the first derivative changes there from negative to positive. So I'm going to point to the 0 and indicate that there's a local minimum there. And then I'm going to find that local minimum value by substituting 0, the x value, into the function. And we did that actually already. I'm going to look up here. I can't remember what the answer was. 9/2 or something, I think. Yeah, we did that when we did the y-intercept right here, right above the box. That was 9/2. So I don't have to recreate that. I can just look up there and just see what I wrote last time. It's not a lot of arithmetic, but you certainly don't want to write a different value for the y-intercept. You don't want mistakes here. Okay, so we've now found the increasing, decreasing behavior and the extrema. If I specifically ask you to find the extrema, here I would want you to say there is no local max. If I specifically ask you to find the maxima and minima, you need to tell me you thought about max and you rejected it. There is no maximum, local maximum on this curve. And I'd want you to address that. Okay, so now let's go to the second derivative. The form of the second derivative, or I'm sorry, the form of the first derivative that I'm going to use is this one, 20x over x squared minus 4 quantity squared, because I think finding the derivative from that will be easier than any of the other forms. So that's still a rational function, so I'm going to use the quotient rule. Low d high minus high d low, and the derivative of something squared is 2 times that something to the first. Then the chain rule kicks in and we have to multiply by the derivative of that inside something. All over the square of low. Okay, so looking for common factors in the numerator, 20 is a common factor, as is a power of x squared minus 4. The common factor is the lower power of the two. 1 is the power of the second one near the end of the numerator. That's lower than power 2, so the common denominator is 20 times x squared minus 4 to the first. Then, from the first term, I factored out the 20, and I factored out one of the x squared minus 4s, so I'm left with the other one, minus. And if you need to mark your paper up to make sure you're taking care of stuff like I'm about to do, that's fine. I've already taken out the 20, and I've taken out the x squared minus 4, so what's left? X times 2 is 2x, times 2x is 4x squared. Please don't obliterate. That's not what I mean by marking it up. Check marks or underlinings and things like that work well, but I really want to see what you had there before you canceled something, if that's what you're thinking of doing. So please don't obliterate, because I need to see that work. And of course, powers on powers, you multiply the exponents. 2 times 2 makes that an exponent of 4. And 1 of the x squared minus 4 in the denominator cancels the 1 in the numerator. So that leaves x squared minus 4 cubed. And a lot of times I write the denominator right at this stage first to make sure I don't forget that I canceled one of them. Okay, so x squared minus 4x squared is negative 3x squared minus 4, which doesn't factor. So that's good as far as that's concerned. Well, I guess I could factor out a negative. Not going to help much, but I like seeing positives instead of negatives inside those parentheses. So that won't hurt. And factoring the denominator, we're going to have x plus 2 times x minus 2, which is then raised to the third power. And if I distribute that, it'll be x plus 2 cubed times x minus 2 cubed. Okay, so we're looking for two items. Where is the second derivative equal to 0? Or when does the second derivative fail to exist? And again, the denominator will turn into 0 when x is negative 2 and when x is positive 2. So those are places that make the second derivative not exist. And the fraction equals 0 when the numerator is 0. So that'll be when negative 20 times 3x squared plus 4 is equal to 0. So you could divide both sides by negative 20. That doesn't factor, so we could use the quadratic formula, or we could, since there's not an x term, solve for x squared and take the square root. And I'm hoping at some point you're going to say, wait, stop. I'm going to go further than maybe you needed to. What's going to happen when I try to solve for x? I'll get a non-real answer, because when you take the square root of a negative number, it becomes imaginary, right? And so at some point in this process, some of you earlier rather than later, at some point in this process you have to say, well, there's no real number that makes that happen. There's no real value of x that when you square it you get negative 4/3. So we don't get any important numbers from equals 0, but in our number line analysis for the second derivative, we still have two important numbers, which will give us information about the function's behavior. And that's going to be at negative 2 and 2. Open circle, because that came from does not exist. Okay, so I'm going to do some substitutions this time. Because of the cubing in the denominator, I've got to be a little bit more aware of what's going on. I think I'll use this version for my substitutions. So if I let x equal, say, negative 3 for that first chunk of the domain, negative 20 times 3 times x squared will be positive. Well, it'll be 0 or positive, and then when you add 4, it will be positive. That 3x squared plus 4 is always positive. So in that position, I'm always going to put a plus sign. Okay, negative 3 plus 2 is negative 1. The cube of negative 1 is negative. Negative 3 minus 2 is negative 5. The cube of a negative number is negative. So negative times positive divided by negative times negative is a negative result. Okay, let's try 0. That's between negative 2 and 2. So negative times positive. 0 plus 2 is positive, cubed is positive. 0 minus 2 is negative. Negative cubed is negative, so that'll be negative. Negative times positive divided by positive times negative is positive. Oh, and by the way, the negative second derivative means that that's concave downward, and this is concave upward when the second derivative is positive. Make sure you can tell that's a second derivative. Okay, then something to the right of 2, like, I don't know, 3. I don't tend to go very far away because it just makes the calculations I'm doing in my head harder. So negative 20 times always positive. 3 plus 2 is 5, 5 cubed is positive. 3 minus 2 is 1, 1 cubed is positive. And the product, negative times positive, divided by positive times positive is negative. So that's concave downward. And again, if I asked you about intervals of concavity, I would want you to write sentences and talk about why it's concave upward, for example. It's because the second derivative is positive there. But in this type of problem, where that's just one piece of a bigger problem, this number line analysis by itself gives you all that information, and I don't need the sentence. I would want you to identify if you have points of inflection. Keep in mind at negative 2 and 2, we have vertical asymptotes. So those cannot be points of inflection because there's no point on the graph when x is negative 2 or positive 2. So if I ask you to think about, are there any points of inflection? And if they are, where are they? If I ask you to address points of inflection and there aren't any, you need to tell me that, because that means you thought about it and rejected the notion. And that tells me you did some critical thinking there that led you to that result. Okay, so now we get to put all that together. And that's quite a bit of information. And unfortunately, it's hard to see all of it at once. So you're going to need to rely on maybe looking back, and I may scroll back occasionally to show things that we had written down before. Or maybe you can just trust me when I draw it, and you can feel like it's valid. All right, so I'm going to number this off by fairly small numbers, or small distances, so I can get a lot of mileage out of each axis that I've drawn. I might be doing a little bit of overkill. I may be giving myself way too much to work with, but that's okay. Okay, so one of the first things we found, and I won't necessarily go in the order in which you found things, just saying, was we found that we had vertical asymptotes at x equals negative 2 and x equals positive 2. And because you have that labeled in the work, which is what I'm going to look for as work, you can label it on this graph as x equals 2 and x equals negative 2 if you want to. I won't require it, but I will require that you've written it down in your work above, as we've done. We also found that there was a horizontal asymptote at y equals 2. And again, you need to draw it. You can label it on the graph or not, your choice, because it is labeled in the work. So if you don't label it in the graph itself, that's okay. Okay. Now, another thing we found were intercepts. So we found the x-intercepts were negative 3 and positive 3. And the y-intercept was 9 halves. That's 4 1/2. 1, 2, 3, 4 1/2. 9 halves is right there. Okay. We'll come back to the symmetry idea in just a second, because after we graph part of it, you'll see that, oh yeah, that is symmetric. Okay, so starting at negative infinity, I'm going to scroll back for this. I'm going to look at both increasing and concavity behavior. So from negative infinity to negative 2, this thing is concave down and decreasing. Can you see both of those at the same time? From negative infinity to negative 2, the function is decreasing and concave down. Okay, decreasing and concave down. Taking into account our horizontal asymptote and our x-intercept, This is decreasing and concave down, right? Decreasing and concave down. Okay, now starting at -2, what's going on? Starting at -2, it's going to be, pick a color over here, hold on. Pick a color that I haven't used yet. It's going to be decreasing until 0 and concave up. Decreasing and concave up. Decreasing and concave up. So for starting at -2 to 0, it's going to be decreasing and concave up, and I'm taking into account my vertical asymptote on the left of that yellow part and the y-intercept I'm headed toward. Then starting at 0, let's use a color I haven't used yet. It starts to increase from 0 to 2, but it's still concave up between -2 and 2. So from 0 to 2, it's increasing and concave up. So increasing and concave up, taking into account our vertical asymptote. Okay, then to end this, from 2 on, the function is, where's my cursor? There we go. From 2 on, it's increasing and concave down. Increasing and concave down. Increasing and concave down. So taking into account the vertical asymptote, it's increasing and concave down. Don't forget to go through the x-intercept. Increasing and concave down. Don't forget to go towards that horizontal asymptote. And there you go. And there's a pretty good graph. The range, oh, I did think about it, yay me. This function goes from -infinity all the way up to 2, but does not include 2 because you never hit that asymptote. Then there's nothing graphed between 2 and 9/2, and it starts up again at 9/2 and goes up forever. So the range should be from -infinity to 2. Don't include 2 because it doesn't ever get there, and then picks up again at 9/2 and goes up forever to infinity. Notice how I can do that once the graph is done. It's not that big of a deal. Let's go up and see if that's what I wrote up there. So I thought I wouldn't remember. Yep, that's exactly what I wrote. It's right there. Right there. So, like I said, the range is usually one of the last things. So when you're doing a list of things, find the domain, find the range, find the intercepts, find the asymptotes, you might want to kind of check them off as you do them, and then go look back through your work second time and make sure you've written every one of those down, as I've done, and again check off. So have like a double check system to make sure you've done everything and addressed everything. And if there's something I've asked about that there isn't one of those, like no relative maximum, make sure you say there isn't one. No local max or no points of inflection. All right, so this is a pretty good example of everything that I might ask you to do on a test question. Now, since you have a graphing calculator, you can certainly type this in your calculator and set up a window so you can see all of that good stuff, and kind of make sure that you're able to get the confirmation that you might need to say, hey, good job, I did it. Okay, let's look at another one. As I mentioned earlier, there is something possible called a slant asymptote, and we kind of talked about that. So that can happen if the degree of the numerator, let's say this is x to the n, I'll call it a sub n times x to the nth plus a whole bunch of stuff, is divided by b sub n minus 1 x to the n minus 1. So the greatest power in the numerator is exactly 1 more than the greatest power in the denominator. That's when you're going to have a slant asymptote. And to find the equation of the slant asymptote, as we saw earlier, we'll do polynomial long division. So for example, this one, if I have x squared minus 2x plus 4 over x minus 2. This one has a slant asymptote because 2 is exactly 1 more than the degree in the denominator, which is 1. So we know we'll have a slant asymptote. To find that slant asymptote, we'll do long division. I'll write up here, that's what you're going to do to find it, is long division. And to do long division, I ask myself a series of questions to get myself through here. So what I think of is looking at the first part outside, the x, what would I need to multiply that x by to get the first thing inside the x squared? What would I multiply x by to get x squared? The answer is x. Then I multiply x times x minus 2, giving me x squared minus 2x. Then I subtract. X squared minus x squared, of course, is 0x squared. I never write that first 0. Negative 2x minus negative 2x is 0x. And again, I'm probably not going to write that, any zeros. So 0x. So I just pull down the 4, and x does not go into 4. So we're done dividing. So that means that this function is equal to x plus the remainder of 4 over the divisor x minus 2. The slant asymptote for this function will be at y equals the quotient part, the part that's up on top of that division bar, the x. And as I said earlier, that's because this part, constant over power of x, will go towards 0, and the rest of it will go towards x. It won't ever be x because that's headed towards 0, not equal to 0. So it just gets, the graph of the curve just gets closer and closer to y equals x. Okay. So the other thing we can tell is this thing has a vertical asymptote at x equals 2. And so if we were to graph this, let me put several marks on here. We're going to have a vertical asymptote at x equals 2. We're going to have a slant asymptote at y equals x. And we haven't done the full analysis of this one, so I'm not too worried about perfection here. But I think I will find what the value of this is when x is 0. So if there's a y-intercept, I'll find it. 0 minus 0 plus 4, so 4 over negative 2 is negative 2. So it does have a y-intercept of negative 2. And let's see if it has any x-intercepts. Is this function ever equal to 0? Well, we've talked about this before. That only happens when the numerator itself is equal to 0. And I can't factor that, so I'm not going to be able to solve it by factoring, which means if it has x-intercepts, I'll have to find them using the quadratic formula. So x is the opposite of b, so positive 2, plus or minus the square root of b squared. The square of negative 2 is 4, minus 4 times a, which is 1, times 4, which is 4. So 4 times 4 is 16. Oh, do you see what's going on here? All over 2a. Whoops, shouldn't write a, because a is 1. 2 times 1 is 2. 4 minus 16 is negative, and so x doesn't have any real x-intercepts, because 4 minus 16 being negative means we're going to get imaginary parts to that, so it's not going to be a real intercept. So we're not graphing any x-intercepts here. And if we did all of the analysis and the increasing, decreasing, and concavity, you'd end up getting this. And we're not doing that on this problem. I'm just showing you the slant asymptote and what that could look like. And then on the other side, it looks something like this. And I should have drawn that vertical asymptote up a bit higher than what I did. So let me fix that. Sometimes you end up extending asymptotes because of what you're drawing. It needs to kind of make sense. So that looks a whole lot better. Okay, anyway, we would have found that it increases, then decreases, and then over the asymptote, it'll decrease and increase, and it's concave for the first part, and concave down for the first part, concave out for the second part, and all that good stuff. If we found all that, we'd have all that information. Plus, we'd know that where the local extrema are. There are no points of inflection on this graph. Anyway, that's the end of this section. I will see you in class.